Okay, hi everyone. This is first lecture. So we start with some uh, essential tools for counting that we'll need in probability and statistics. And um, this first one is everywhere almost. So it'll be interesting to see it come back up. Uh, Often you don't even really think about this, but this is underneath so much. So it's called the principle of counting, and it states that if you have two experiments, let's call them experiments, although maybe not in a traditional sense, but I have two experiments. The first one has M outcomes, M, and for each of these, then I have another experiment that has N outcomes. So we'll do several examples, but for each of the M outcomes in experiment one, there's a second experiment that's performed and that has N outcomes. Then taken together, there are M times N outcomes possible in total. So to be very clear after a few examples, suppose we flip a coin and note heads or tails, and then independently of whether it's heads or tails, I always also roll a six-sided die and observe 1, 2, 6. Then this is M is 2, N is 6, because for each I always do this. So total outcomes equals 12. Okay. In baseball, there is a team, 9 players, and there's always they're assigned to positions, and there's always a catcher and a pitcher that has to be. So, and one of each. So the Red Sox have 3 catchers, say on their current roster, and 11 pitchers. So there are 33 MN catcher, pitcher duos, combination. Okay, now this, you don't think of this maybe as an experiment in the traditional sense, but you can think of it as, managers picking a catcher. In a sense, that could be thought of as an experiment. What does he pick? And then he picks a pitcher, or she picks a pitcher. Maybe someday the Red Sox have a woman manager, so picks 3 catchers. So out of 3 catchers, picks a catcher, and then for each picks a pitcher. And then so there are MN total possible combinations. Okay, let's just do maybe one more. This extends it a little. So how many how many 10-digit phone numbers are possible if first and fourth digit cannot be 0 or 1. Okay, well, let's see, I have 10 things now, right? So let's just do this in a little bit of gore here. Let's take this, the point of it's not to actually get the number so much as to understand what's going on. But so I have 10 spots here, and there's 10 possibilities for all, but this one there's only 8 possibilities, right? And then there's 10, 10, 8, 10, 10, 10, 10, 10, 10. Okay, so just multiply them all out. But how do we see that that's part of the principle of counting? Well, you could say for the first two, clear that the first two, there's 80, right? So we can note by PC, there are 80 possibilities for first two digits. Okay. Now by PC again, since there are 80, I can now look at the first two as a single outcome, right? So then there are m equals 80 and n equals 10. So mn equals 800 possibilities for first three. And we can go like this, etc. So, etc. So for the first four, there's 800. So the next one would be m equals 800. And then n equals 8 this time, right? So first four would give me 6,400, and then etc. And we end up with, in the end, we end up with, until we get 10 to the 8th, right? So 64 times 10 to the 8th power. Okay, possible in total. Okay, all right. Okay, so principle of counting feeds right into the definition of what a permutation is. So a permutation says, permutations, so we could say, let's see, NPR, this is equal to number of permutations. There's other ways. Usually I think in the book just writes it in English. Number of permutations of n distinct objects of size r. Okay, well, if I have n, let's say, for example, r is 2, so I have np2. This is just saying how many ways can I arrange n distinct things, 2 of them. So there'd be n possibilities here, right, and n minus 1 here of the n distinct object. So this is principle of counting again. So by PC, np2 is equal to n minus 1. Now, why is it n and n minus 1? If they're all distinct, and I pick 1 for n, then the principle of counting says if for each n there are this many possibilities. So once I pick one, there are only n minus 1 left. That's the key. But they're all left. And so each outcome from 1 has n minus 1 outcomes from 2 that can go with it. All right, so if we iterate in this way, we can get, so note NPN, if we want all of them, although we don't usually write that, we just say the number of permutations of n distinct objects. This is just equal to n minus 1, ... 2 times 1. So this is n factorial. So for example, how many permutations or arrangements of the letters let's say C-U-P are there? Okay, well, if I don't specify of size, certain size, it probably means all. So the answer is just 3 factorial, right? So that's the solution. So, you know, look, there's 3 possibilities here, And then for each, there's 2 here. So how could we draw this? So there's 3 possibilities for the first. So you could have C, U, or P. If I have C, then I can have U or P here. There's only 2 possibilities left. Now this, there's only 1 possibility left, right? P. And this, there's only 1 possibility left, U. So we get this multiplying tree effect here. And now this goes just to P, this goes just to C. And finally this one, CU. And this goes to U and to C. So we have cup, we have kapu, ukup, paku, what? Kapu, ukup, upuk. Okay, I'm silly. You can see it's all right though, right? They're all right. They're all different. So this is what's going on. It's the principle of counting. Suppose, example, I have a class of, say, 12, and we need to elect a chair, a student chair, and student treasurer. Well then, how many possibilities are there for the chair? 12, right? Any student could be the chair. And then for each, because they can't also be the treasurer, there's 11 left over. So there are 12p11, which is equal to 12 times 11, which is equal to 132 possible assignments or election. So possible assignments. Okay, so this is all the principle of counting. This is called permutations. Let's take it. Okay, we have to stop. We'll continue in another video.